Hello. So now we're going to do this problem. It's a fencing problem. Okay. Let's read it together. Suppose that Jessica has a rectangular plot of land which needs to be fenced. Okay. Suppose that the perimeter of her plot is 20 feet. Suppose, moreover, that the two long sides are parallel with the prevailing wind and the two short sides are perpendicular to the prevailing wind, and consequently it costs $5 per foot to fence the short sides and $3 per foot to fence the long sides, and it costs $72 for the whole fence. What then are the dimensions of the rectangular plot? Okay. Okay. So the key thing here is that we have a rectangular plot, and there's a characteristic that two of the sides have and two of the sides do not have. Namely, two of them are perpendicular to the prevailing wind and two of them are parallel to the prevailing wind, and that leads to a difference in the cost of the fencing per side. And so that is going to necessitate, in other words, for us to satisfy two constraints, and it is this fact that we're going to need to satisfy two constraints that's going to lead to the two equations. Okay. And so let's begin by drawing a picture. Okay. Okay. So what I'm going to do is I'm going to say, okay, I have this rectangle. It looks like this. Okay. And let L represent the length of the long sides. And let's let S represent the length of the short sides. So let's label this, okay? L is the length of the long sides. And S is the length of the short sides. Okay? Okay. So now what we want to do is we want to find out how we can use the constraints that we are given to set up an equation for this problem. It tells us in the statement of the problem that the perimeter of the plot of Jessica is 20 feet, okay? And so we have to remind ourselves, what is the perimeter? The perimeter is the length of the boundary. So in this case, it'll be this side's length plus this side's length plus this side's length plus this side's length, okay? So in other words, right, if we want to do that, we'll see that that's L plus S, right? Which we can simplify. If I have L plus L, that's 2L. If I have S plus S, that's 2S. So this simplifies to 2L plus 2S. And what does that equal? That equals 20 feet, as they give us above there, right? 20. So that's our perimeter, okay? Let's call that feet, the perimeter. But then they tell us that there's a cost for the long sides and there's a cost for the short sides, and we know the total cost. So let's call the cost C. Okay? We know that, let me see here. It's $5 per foot to fence the short sides, right? So it'll be 5S plus 5S, right? Wait, what? Yes, exactly. So it'll cost 5S to fence this short side, and it'll cost 5S to fence this short side, for a total of 5S plus 5S. And then it's $3 per foot to fence the long sides, right? So it'll be 3L to fence this side and 3L to fence this side. So plus 3L plus 3L, which will give us 10S, okay? And 6L. And of course, that's going to give us the 72. Okay, $72 to fence this whole thing. Okay. So as a result of these considerations, we now have a system of equations that captures this problem, namely the following system. Okay, 2L plus 2S equals 20, and 10S plus 6L equals 72. Okay? Okay. So now what we're going to do is we're going to solve this system of equations. Okay? So let's do that. So the first technique I'm going to do is I'm going to use the substitution technique to solve this system. And then afterwards, I'll show you what is called Gaussian elimination to solve the system. Okay, so I'm going to solve it once first, and then I'm going to solve it again, so that you can see these two techniques being used on this system. Okay. Okay, so let's begin. So for substitution, okay, what I'm going to do, this is also referred to sometimes as elimination. Okay, not Gauss elimination, just elimination. Okay, but we're going to call it substitution for this part. And what I'm going to do is I'm going to look for one of these two equations that seems right for us to isolate one of the variables. To me, this first equation looks better. So from the first equation, okay, we can see that 2L plus 2S is equal to 20. So what I can do here is I can subtract, let's say, this 2S to the other side, minus 2S, minus 2S, and I get 2L left on the left-hand side equals to 20 minus 2S, okay? And then I'm going to divide both sides by L to get the L by itself. Wait, did I say divide by L? Divide both sides by 2 here. Okay. So then here, you can see that on my left-hand side, I'm going to be left with just L. And on the right-hand side, I'm going to be left with 20 divided by 2, which is 10, minus 2 divided by 2 is 1, S. So I have this relationship between the variables L and S from the first equation. We can now use this in the second equation to replace this L and thereby create an equation only in terms of the variable S, which will then allow us, of course, to solve for the variable S, and then consequently when I plug it back in here to get my value for L. So L equals to 10 minus S, okay? So now let us substitute into the second equation, okay? Right, I'm going to substitute in the second equation, this one here. So I have 10S plus, right, 6 times, what is my L? It's 10 minus S. So I'm going to put that in parentheses here. Now many students might forget to put this parentheses and might end up making a mistake here for that reason. Okay, so notice what just happened here. There is no more L in this equation. This equation is in one variable, and it's a linear equation, so we're going to be able to solve it, okay, provided it has a solution. And moreover, that's why it's called, that's why some authors call it as the elimination method, because you eliminate one of the variables, okay? So now, what we can see here is that I have to simplify the left-hand side before I can solve this equation. What is apparent here is that I'm going to have to perform this multiplication first before I can do anything else. So in order to do this multiplication, what I mean is I'm going to have to apply the distributive law. So it's going to be 6 times 10 will be 60, and then 6 times negative s will be negative 6s. So I'm going to have 10s, okay, plus 6d minus 6s equals 72, okay? And now what we can do is we can simplify the left-hand side by combining these two like terms, the 10s and the negative 6s. Okay, let's do that here. So 4s plus 60 equals 72. Right, why 4s? Because the 10 minus 6 is 4, and so it's 4s, okay? Now I want to get the s by itself, right? So what I have to do is I'm going to have to subtract this 60 to the other side. Minus 60 minus 60, okay? On the left-hand side, it's gone. I'm left with 4s, and that's equal to, if I look at 72 minus 60, I can ask myself, what is 2 minus 0? That's 2. What is 7 minus 6? That's 1. And then what I can do here, finally, is I can say I have 4s equals 12. So I'm going to divide the left by 4. I'm going to divide the right by 4. And I know that this is going to give me s. And what's 12 divided by 4? 3. So I have here s equals 3. Okay? That's the length of my short sides. And now, from over there, I can see my L is 10 minus s, but we know now that s is 3 here. So it's 10 minus 3, so that's 7. Okay? So I can now state the answer to this problem. So the answer to the question is, the dimensions of Jessica's plot are 7 feet in length and 3 feet in width. Okay? So here we have used the substitution technique, and I want to make the following point. What we just did was we took the first equation, we solved it for one of the variables in this case L, and then we substituted that expression for L in terms of s into our second equation, and then solved it for s, and then plugged back into the relationship between the L and the s that we got from our first procedure. One of the questions you might have in your brain is, well, David, could I have solved the second equation for one of the variables, s or L, and then used that expression as substitute into the first equation, and would I have gotten the same answer? And the question is yes, as you can easily verify, and it would be good practice if you verified that yourself. Now the key thing you do have to realize is that what we can't do is we can't substitute. So for example, if we solve for L in this equation, we don't substitute back with that expression into the same equation. We always have to substitute into the other equation. Okay? Okay. Now we're gonna resolve this system of equations using Gaussian elimination, and let's do that right away. And so basically what Gauss elimination is a way of transforming a given linear system, such as the one that we got from the fencing problem, from Jessica's fencing problem, into an equivalent system, that is a linear system with the same solution set, but in such a way, the way we're going to do it, in such a way that it brings us closer to a solution, to a system with a solution. Okay, you're going to see that the reason why it's called Gauss elimination is that we're going to use these rules to basically transform the system into equivalent systems that basically in one equation we get rid of one of the variables, we eliminate one of the variables, and thereby arrive with an equation that we can solve for one of the variables, and then we're going to be able to use that value to back substitute to get the value of the other variables. In this case, there's just two equations, so once we eliminate one, we get the other one, and then we just solve for the remaining variable. Okay? So in other words, the Gauss elimination is a procedure, is a set of rules and a procedure that allows to take any linear system and transform it into an equivalent system. Okay? We can interchange any two equations. So this system is the same as the system that I would get if I was to interchange these two equations. Okay? That one I think is quite obvious. Okay? The second one is more interesting. Multiply any equation by a non-zero constant. So what that's saying is I can multiply this first equation by some number, and that will not affect the solution set of this system. Okay? And finally, I can replace any equation with the sum of any two equations from the system. Okay, so if I were to take this first equation and I could replace it with the sum of these two equations, and that would give me an equivalent system. So now the key question that comes to mind that I want you all to think about is, or that I know that you guys are all thinking is, well, David, what are we going to do? How do we use these rules to solve this system? And here's the way we're going to do it. I look at the system as written, and I say to myself, aha, what if I multiplied this first equation by -5? Then this first coefficient, this 2 in front of the L, would become a -10, because if I multiply this whole equation by -5, this will be -10, and then you'll see that in a proximate step that will come later, I could replace the first equation or the second equation with the sum, and because that one's -10 and this one's +10, I could eliminate the variable. But okay, so now we have a problem though. I just noticed, and I'm glad I noticed it now, and I want you guys to notice it too, that this is the L and this is the S, so we couldn't have done that, right? So what we're going to have to do before we apply the elimination is we're going to have to interchange the order of these. This is 6L plus 10S, okay? Okay. That's one of those moments where you're like, whoops, did I almost make that mistake? No, yes. But the first thing you have to do whenever you're doing a Gauss elimination problem is you have to verify that all the variables are in the right location, okay? But I'm glad we also had the discussion, because you'll see more or less what I'm about to do. Now that it's in the right order, okay? So let me also state, that's not a consideration we had to do for the substitution technique, right? But it is important for the Gauss elimination. So now here, using the same kind of reasoning, I can say, aha, what if I multiply the first equation by -3? Aha, then I'll have -6L, 6L. So in a proximate step, I'll be able to replace one of the equations by their sum and hence eliminate the L. So let's do that together. I'm going to notate what I'm doing as I do it. So I'm going to say, okay, I'm going to say -3 times my R1, my first equation, will be my new R1, okay? This is going to be my shorthand for performing this kind of calculation. Okay, so if I multiply this first row by -3, I get -6L, okay, minus 6S, because -3 times 2 is -6. And then that equals to -3 times 20 is -60, okay? And then I just bring this down as is. Now, as we had mentioned before, what we're going to do now is we're going to replace the R1 with the sum of the R1 and R2. So my R1 plus my R2 from this equation is going to be my new R1. But I'm not going to do anything to my R2, okay? So I'm just going to leave it as is. Or let's divide it by 2 to make the numbers nicer. So we'll multiply the second equation by 1/2. That'll become, so 1/2 of R2 will be our new R2, okay? And so, by the way, I also recommend when you're doing your equations, when you're doing your solutions, I want you to notate what you're doing from step to step. You can use my notation, or you can use any notation that's consistent and dependable, because when you're doing these problems, if you notate your work properly, then your notes will become like your own study guide, so you can prepare for tests and stuff, okay? So let's do that together. So so I'm going to replace my first row in this new equivalent system with the sum of these two. So if I have -6L plus 6L, that's gone. Boop, gone. -6S plus 10S, aha, that's 4S. And that's going to equal to -60 plus 72, boop. When I add those, I get +12. Okay? Then I'm going to multiply this one by 1/2. So 3L plus 5S is equal to 36. We could see that by doing the long division on 72. Okay? But what I want you to observe is here. Notice the way the equation looks like now. Sorry about that, I was stuttering there. In this setup, we have the first equation has been transformed by the Gauss elimination procedure to one that is only in terms of s. And so we can see here this first equation, 4s equals 12. If I divide both sides by 4, I get s equals to 3. Okay? And then I can use that value in this second equation. 3l plus 5 times 3 is 15 equals 36. Let's rewrite that here. 3l plus 15 equals 36. Okay? Okay. So how am I going to get the L by itself here? I'm going to subtract the 15 over. Minus 15. Minus 15. Okay. 6 minus 5. This 6 minus 5, that's 1. 3 minus 1, that's 2. And I'm left with 3L on the left. Right? And then if I divide both sides by 3, I can get L equals 7. Okay? And so this is the same values that we got using the substitution technique. But now we've gotten them through the Gauss elimination. Now let me make just a brief technical point. It's not really that important, but what you need to see about this form is that basically it kind of looks like a triangle. Now strictly speaking, in order to say that this matrix is a triangular form, I would have to interchange these so that the diagonal is like this. But in any case, the most important part that I want you to get from here is that by doing the elimination procedure, we eventually end up with, or we want to end up with, an equation where one of the variables remains, where one of the equations remains with one of the variables, or we want to go as far along that as possible, as far along to that as possible. We'll talk about those technical details in more detail later. Okay, it's going to be something called the Row Echelon Form. But you can see here that once you get the equation with one variable by more or less by itself, then you can perform the substitution that gets the solution. Okay? Till next time, I hope you've enjoyed this problem, and I'll see you again soon. Thank you.